Is to host a talk by Professor George Smoot. He's one of us, is IAS Professor at Large. And George, I guess, in the physics community, we not need introduction. He is world famous for his work on cosmology, in particular for his discovery of the anisotropy in what we call the microwave background radiation in that permeation in the universe. That actually tells us something about how the universe began. Maybe from a small pond, and then it Big Bang, and then it inflated, and it becomes what we are today. But I think in recent years, I think Professor Smoot has broadened his interest into other fields, including how we can improve the well-being of mankind. And we know that since time immemorial, I guess mankind have tried to, have longevity. So I guess starting from the very old times, the pharaohs in Egypt, the emperors in China tried very hard, and I don't think they have that much success. But today, with new technology, I guess Professor Smoot is going to give us a conceptual framework to see how modern technology can help us achieve what was deemed almost impossible in the past, and maybe we can do it in the future. So without further ado, let us welcome Professor Smoot.
Thank you very much. I'm actually still trying to do some etymology. Now I can blame a little bit on one of the slides for so a little rough, because I was trying to do a bunch of tensor calculus for the last 2 days, and I'm kind of old and slow at it. But there are still interesting things going on in cosmology too. So what I'm doing now, this is the third in this series, what I call the ring lectures. The first lecture was that we have entered the singularity, which is something John von Neumann forecast 3/4 of a century ago, that when the rate of change of technology becomes faster than the rate at which humans and human society can adjust to it, human institutions are going to be swept away, and human laws are going to be swept away, and new things are going to come. And you're going to see that when you think about, if you bother to think about, the implication of people not dying. That has to change a lot of laws, has to change a lot of things. So if you decide not to die, then you're going to have to change some laws in some rules of society and some institutions. But that's the philosophical for the future. So when you enter the singularity, you don't solve today's problems with the most advanced technology you can find. You think about what are the real problems are going to be in 5 years, and you think about what technology is going to be available in 5 years, and how that will solve that problem. We're solving a lot of problems that we deal with, like how does a doctor diagnose something, with the cutting edge technology of AI or some of that kind of thing. You eventually just have to think, what are our problems? Our problems are, we'd rather not get older and die, or get older and be sick. We would like to maintain the vitality and vigor of youth for as long as we want. So that's a problem that's going to be around in 5 years, where some of these other problems are not going to be there because we have a different way of doing it. There are 5 technologies. The previous lecture, the lecture on how to create stem cell therapy centers that are automated and safe, and all the therapies that go with them. That's one of the tools you'll need. AI is one of the tools you'll need. Some of the other things I'll describe and what's going on here. So that's the punchline from what you're supposed to learn from this talk. Okay, so what's a digital twin? A digital twin has been around in engineering for quite some time. And the earliest ones that I kind of heard about were digital twins for these great, huge windmills that produce power. And there's a physical windmill that produces power with a lot of sensors and things put on it. And there's a digital twin that is a model replicated in the digital world of that puts that information in and sees what the stresses are, sees when the blade should be feathered, all this kinds of stuff. The first one I ever saw in detail is a digital twin of a turbofan. Now, when you're on an airplane, usually in the tail, up in the tail of the airplane, is a turbofan. The turbofan is a jet engine that also is an electrical generator, and it generates the power that the airplane uses, and you use when you're on the airplane with your phones and computers and other devices. I went to the place where they were developing a new generation of these turbofans. They had built into this huge building, a wind tunnel, so they could simulate a plane flying. And there was a room with 50 or 100 engineers, all looking at the computer screens, looking at various sensors, looking at various parts of the model, seeing how the turbofan was performing. Was it doing well? Was it going to be stable? Was it going to last a long time? And they were doing that. Now it turns out one factory produces about 70 or 80% of all the turbofans used in the world. More companies have been cranking out engineers to work in this factory because that was the biggest employer in the town, right? So, but it was very impressive how detailed and how sensor mounted it was that I saw that. There are digital twins for buildings, so that you can see whether the building is behaving, what the energy efficiency is, how you need to circulate the air. There's digital twins of a lot of things in the world. Almost all of those are engineering models, and they're all a lot simpler than a human digital twin is going to be. The human digital twin is going to be very high level AI, and the physical modeling will have to go to extremely high resolution. And later on you'll freak out when I tell you how high resolution, but then you'll realize it's not that far out of reach for us to do that. Okay, so we're going to do 3D, size, weight, composition, everything else modeling. We're going to have stuff on the model levels at the system level, and the organ level, and the cell level, and the molecular level. We've got to have all of those models in there, and some of them we can kind of treat thermodynamically and say this is the average, or we're just looking at the difference between what your cell looked like 2 months ago and what your cells look like now, what your cells look like 2 years ago, and what they look like 20 years ago. But you're also going to be monitoring people's behavior and lifestyle, because there's a lot of epigenetic factors that are involved in your health, and your emotions and your feelings, because those are also epigenetic. So this is going to be invasive, right? And you're going to measure the level of excitement you have, how engaged you are, right? And what your preferences are for various things. All of those things are going to go into the digital model. So how do digital twins work? Basically, you're going to do all this detailed modeling, and you have to put in the model everything that's really relevant to the machines that are operating. Now, if you take a non-mystical viewpoint and look at human beings, they're just big, complicated sets of machines, many machines, a lot of things going on, but they're big, complicated sets of machines. So it's going to be a really big digital model, but it's going to be same kind of function as that. So you're going to be looking at the human health performance in real time, and you're going to be doing sampling of people's health at a regular basis in order to see what's going on. Once you understand that, and once you have a few 100,000 people in your digital modeling, you have a tremendous database that you can cross-correlate and learn about the stochastic nature of things, and learn about you'll learn about the behavioral nature of a bunch of things. Figure out what the optimal performance is. You can figure out how to make the physical safety better and the health better and so on. So you go on. So this is what you do for engineered systems. This is what you're going to be able to do for human systems. Humans are just much more complicated machines. This is not new. People have been thinking about digital twins for things. There was, in 2013, a French company that developed a 3D digital model of the heart, and it had 200,000 tetrahedrons making up the surface of the muscles of the heart and the inside of the heart. And they used this and the computer models to simulate how a heart would go in order to be able to see how you respond to devices like angioplasty rings or pacemakers or other things like that. So I'll show you a little picture of this. You can see it's high enough resolution. You don't see those little tetrahedrons that make up the heart. You just see what looks like an idealized heart. Right? They're doing this to see how the heart actually behaves. What happens when you put it under different stresses or use different medical approaches, then you can see how it responds and what happens. And what happens if you have an unusual side heart. So you do this as part of a real 3D model of human beings. This is focused on the heart. If you remember, heart disease, coronary diseases and circulatory diseases are the #1 killer of human beings. Number 2 is cancer. Number 3 is medical error. You go down the list. Well, I mean, the doctors don't report that, but you have to have the requisite technologies. That means you need some nanotechnologies. Well, guess what? We're in the nanotechnology age, just starting. We need sensors and actuators and things to be able to monitor people really carefully and feed back the digital model. We need artificial intelligence algorithms. Guess what? They're coming pretty soon. Right? We've got some that are pretty good. We've got some that are more. Why do we need it? I'm going to show you the scale of what we're talking about. So you need the real-time data plus the physical model, the other person. You're going to need some past data. Best thing that could happen is if your parents saved your umbilical cord, stem cells, you would have DNA from when you were in your most original state. If you sample enough DNA, if it's cheap enough, you can sample enough DNA, you can kind of reconstruct a rough idea of what you look like when you were in your closest to your original mode. What things are having problems, what things are not having problems, what kind of treatments you might need, make a model of how those treatments will behave to you, and then take the one that seems like the best course of action and see if it's a remediary, and watch for what's going on. And this is a whole set of things that you need to keep track of the person's health, and you need to track what kind of fixes you're doing to try and keep them effectively young and vital. The complexity is aging doesn't begin at 50 or 60. Aging begins at -1. You wanted your parents to have been well fed and well in good shape. You conceived, from the time you're conceived on, you have a human genome and mitochondria, a bunch of things like that, that then you're trying to keep not from aging severely. It has to age to a certain point, you gotta get to your 20s, so you're kind of a grown adult, and then you need to keep it from aging anymore. Here are people thinking about how you do it, how do you make a model in one direction, you take the person and how do you have to make more than one digital copy or whatever it is. But one of the things is, you would like to do this to a large sample of people. So you have a whole bunch of digital twin aggregates so that you can do statistics across populations and see both that you've got the stochastic fluctuations that are happening and are right about it, but also to see what the whole overall general trend lines are, what treatment and what applications have actually caused things to improve and what have made things worse. But you want a whole population of digital twins, and you have to have some device or some system that is correlating the data across the digital twins. How big a job is this? Well, when I started estimating how to do this, you got to do stuff on the system level, at the subsystem level, and at the cellular level, which is the DNA level, and the molecular level. And you have to do that through a lot of modeling. And there's at least a couple of thousand things you have to keep track of, but I'm going to tell you it's a lot more than that. And you have to think, how often do I have to sample this and make sure that I have sense of it? And I was first guessing that the way people age is roughly once a month for their entire 100-year life or their entire 200-year life. You're going to have something like 1,000 or 2,000 set of timestamps that you're going to go through where you're going to run big simulations, you're going to do all kind of stuff. And you're going to have outcomes, different kinds of diseases and different kinds of senescence, death, that you're going to want to keep track of and project what's going to happen at the end. Right? Now, your goal is to stop people from getting there, but at the end, you've got to have the data of what's going to happen and model of what's going to happen so that you know how to intervene in the real time. One of the things that you realize you would like to be able to do at the end is do an entire scan of the human body where you look at every cell and you look where it is, what kind of a situation that cell is. Is it got DNA changes? So you want to keep the difference between the old model you have as the cell's DNA and where it is now. The other kind of proteomics that are there, plus the mitochondria. So you're going to need to keep track of 10 to the 15 cells, and you're going to need to take some number of bytes per cell. Right? If you do differences, it's not as many bytes as you want, but it's going to be a number of petabytes. If you look at how the cost of storage is going, it's fortunately been dropping about a factor of 10 for 2 years. If you have 10 to 15 cells, it's gonna be possible to store that information. So we had a talk on Wednesday by Dr. Ellie Ursher who's at Ludwig Maximilian University of Munich, has his own company. He's the guy that made the transparent mouse. And he does scans of all the cells in the mouse and maps them. And so he gets petabytes of data already. It's expensive. It takes a lot of number crunching, but that's already being done. Now, as a human being, you don't want to be made transparent and put in water and scan, or in a solution that's matching the direction to be scanned. But that's what they do, and it's very impressive. So one of the things the technology we need to do is develop how to do that with a combination of double lasers or an infrared or something we can look inside of people now, and still have enough resolution to scan and see what's going on in each cell. But that's the kind of goal, longer term goal. You can get by with samples at the beginning, but eventually you want to be doing it for everything. So there will have to be stations where people can go and get scanned. And the question is once a month too much? Is once a year? It probably is on the scale at the beginning of once a month, but we'll see. So it's a big deal. You're going to have to run a large number of simulations of your well-being to see what the likely outcomes are, and is there anything that needs some fixing up? That we're going to have to send in special molecular scenes to fix that up, and I can tell you what it is. So, and then we're going to have some master program running this cross-correlating against all the digital twins. You'd like to have 200,000 or 1 million digital twins that you can cross-correlate from if you really want to do this right. If you call up one of the cloud storage places and say, I got a petabyte of data I want to store, they say, well, you need a budget of $1 million over 5 years. Well, if I wait 2 years, it'll be 10 times less, according to this guy. It isn't going down quite that fast. That's what that second curve is, a little bit of curl down there, because people like to make a profit. To process that data is also going to be similar cost, but not quite as much. And that's why we're not ready for it. We can't extrapolate things getting a factor 10 better in 2 years. It's not inside of our knowledge. I'm guessing it's early cost. If a group of people got together, or a company got together and created a digital twin cloud group, so that you don't have to maintain your own data storage, you trust them enough that you let them maintain your digital twin. It's going to cost you roughly $5 million for 5 years. So about $1 million a year to do that now. So there's enough rich people that 200,000 people can afford to do this easily. There's maybe 1 million people that can afford to do this at some strength. So we're already in the ball game if you can convince people this is the right kind of thing to do. And then you can, as you run it more, things are going to get cheaper, and it's going to get more and more people have this available to them. Here's the way doctors look at it. A skin of the sky without a lot of stuff. But it's all the muscles and all the stuff, right? And they're thinking about medicating and monitoring and testing and sensors and so forth. Only down here at the bottom are the omics, the genomics, and the other kinds of things. But if you make a digital twin, it's going to have all that information in it. You've got to think about what you're wanting to predict, what you want to diagnose, what prognosis you want to do, how you want to optimize it. Do you want to track diseases? No. Doctors track diseases. You want them to be healthy. You want them to be young and vital. How can you make sure that's happening? So we'll get back to that in a minute. But so this is the doctor's eye view. This is the digital space eye view. That is, you're going to have large-scale groups of twins. You're going to be able to study vascular systems in a lot of details. Still a leading cause of death in the United States and both countries. And it's connected to a number of other things. It's like your skeleton and your muscular systems also are affected as you age, and they end up having feedback into the other systems. There's a crosstalk between the various things, and you need to put all this together. And none of this is that complicated. It's really hard for a human to keep track of 1,000 things, but it's not hard for a simple AI to keep track of 1,000 things and look at the cross. I mean, they have trillion coefficients in the neural net. I mean, they can keep track of a few more things. It's not so hard. You can start thinking about, wait a minute, if this is going to be run by doctors, is this going to be run by governments, is this going to be run by companies? How do you have to have a structure in terms of the software so the patient has access to some of the stuff? Some outside providers have access to some information. Some government people and people doing research. How do you do that? It becomes a complicated who do you allow to have access to these data, right? Because it's like saying on the internet, if they're not charging you for the service, you're the product. Right? This data is going to be extremely valuable. It's you. I mean, if your DNA is all, your cells are stored in cryo storage and the DNA is tracked, that's as much you as your body. Right? So there's lots of different things. Somehow we always put a human expert in these things, but the fact is, the AI agent is going to be doing almost all of this stuff because there's way too big a scale for a human to have 1,000 factors in their mind, but it's no problem for an AI to do that. So we're going to do digital twinning, and we're going to do digital twinning spanned in another dimension. And we need to do that in order to be able to give people the found use, basically. I found another thing where these people were talking about creating a perioperative human digital twin. They wanted to know how are they going to operate on this person, how is they going to react, how is it going to behave, what's going to happen. They make a digital twin, they do a digital operation. Here's the things we needed to know. I added some other things over there, like the DNA data, the telomere links, the mitochondrial status, and various organ systems. There's a whole lot of things you have to keep track of. I don't have to keep track of all of those. The computer has to keep track of all of those. I'm offloading the hard stuff or the detailed stuff to the digital agent. You're going to see you have a lot of ethical questions come up. Normally we treat humans as special. We actually have a lower standard of conduct and behavior and effectiveness for humans than we do for machines or other things. When will you pick a robotic surgeon over a human surgeon? Well, you're going to pick the robotic surgeon over the human when it's your body, and the robotic surgeon has a much higher success rate than the human surgeon. And that's already happening when Waymo Taxi comes to Hong Kong. Are you going to ride a Waymo Taxi, or are you going to ride in a human-driven taxi? Right? Well, depends on what you get used to, but the answer is your safety is clearly better the fewer human drivers on the road and the more automated drivers on the road. Humans have a double standard, and they let humans do a lot of crazy things, but in fact, the doctors really, medical people, it's not just doctors, medical people, are the third leading cause of death. We're going to have psychological stuff in your model? Yes. It's going to invade your privacy? Yes, because it's going to be a digital model. It's going to know everything you like to know. The problem you see is that there is roughly 5% of the people account for half the medical expenses. 1% of the people account for a quarter of the medical expenses. That means if you have a given sort of budget for your social structure, you want to think, how do I optimize the health of the whole population? Or do I say, I gotta have every human is sacred and I gotta try and save everyone? Right? That's the crisis that always comes in the medical situation. There's another set of people that I saw firsthand, that is people who are drug addicts, alcoholics, or have psychological problems and don't have medical insurance. And they do some things that are terrible. I was at the San Francisco University of California, San Francisco campus. It's one of the top things. And I was there or to take somebody there who had to have an operation. And that was a great place to have the operation. And when I was in the waiting room, this guy came in yelling and screaming, blood streaming around and everything like that. And he had taken drugs and thought that flying out of the third or fourth floor window was something within his purview. He did. He landed in a car and destroyed the car, hurt himself some, but fortunately didn't break any major bones or anything like that. But he had to go to the emergency room in the hospital, and he was a danger to the nurse. He was kind of very danger to the nurses and the doctors. They were trying to calm him down and treat him, and they thought, oh yeah, we know this guy. This is the third time he's been in here in the last 2 months, right? Because he thinks he likes to take drugs and can fly. Well, those guys are people who are sort of self-harming, and yet they're using a huge fraction of the medical resources. It's an ethical question. Do you try and treat everybody, right? Or do you limit how much treatment you give those people so that you have enough for others? So that's the joint decisions that are made all the time now. But when we have the human digital models, it'll become a more complicated question. And human digital models will decrease in price as time goes on, but you need to build a first set. So you can see this health treatment is going to become a big issue because people will want good health and they'll want good vitality. I had to ask this in a more functional or separate question. I have to ask the big question: what is life? And there's a lot of people's opinions about what life is. Biologists have said all living things have 8 characteristics. Right? Everyone's off the bottom here, but sorry. I don't know if I can help you. I try to make a really simple definition so you can have a broad view of what is going to be necessary to make it so that you remain young and vital. The answer to first order is life is a set of information that's stored in molecular form, mostly DNA, but some stuff in mitochondria, some other stuff, that provides a prescription on how to take it and create a region of lower entropy so that you can protect that information in as original form as you can. What that means is you take stuff from your surrounding, you bring it in, you burn it up, you use those resources, you create a bunch of entropy, which you then throw out into the environment. Now the problem is your machines, your molecular machines, are not perfect because some of them depend on thermal activations and things that are going on, and then locking stuff in. So then if you create more entropy, you're going to end up with a little bit more entropy left in the cell when it's doing these things. And so the more entropy you're creating by processing stuff through your body, the more likely you are to build entropy in your body. And this building of entropy in your body is going to lead to the senescence of your information, your DNA, and so forth. And so the more involved the life form is, it turns out, if you look across a lot of different life forms, the more likely it is to be producing entropy at the maximum rate. That is, life forms that eat up stuff from the environment and spew it and the waste products and the entropy onto the environment, they tend to be more of them. The evolution tends to favor them, right? And in fact, there are some things like chlorophylls that have reached the point where they're maximum entropy producing. Not only do they do good things and take light and turn it into a convenient form of electronic engineering, they also do it at a rate which produces a maximum entropy out in the rest of the world. But that's another thing. Humans have done a lot better than that. We built machines that produce entropy at a much higher rate. the humans have produced entropy at such a high rate, you can see it from satellites. It's another thing. But that's not in our bodies. We got agents on the outside doing something for us. Advanced life, when they've gotten so good at doing this, they've found that extra production of entropy that goes to the outside world, they have to guard against it. They have to add additional mechanisms to the systems inside of the cells in order to correct and remove part of that extra entropy. So we have extra things that repair DNA strand breaks, that repair other things that are in our body. And it's when these extra repair mechanisms fail that you start failing more quickly. So generally for aging, it turns out you have to have several things fail before the cells can't really function anymore. But there are a lot of things that fail in cells and make the cell less vigorous and more senescent, and eventually become a dead weight or a load on the body and something like that. So I won't talk about what it means for AI, but it's very parallel. AI has certain laws it has to follow, which is the computer is stuck in, and then it has information on how to process that information and how to come to conclusions. It hasn't quite gone the next step, but it's not so different from life. And okay, so how are we going to learn? We're going to learn because we're going to look to see what are the major factors in causing lifespan or aging. I use lifespan as a proxy for health, temporary health, or whatever it is, or the arc over a human's life. And if you look here at the log of the body mass from 100 kilograms down to 10 to the minus 8 kilograms, the metabolic rate, and you see it follows two power laws. It means that the molecular machineries have discovered a couple of different ways of running, and they know how to do that. If you look at this for brain size versus body mass, we put it here because we like to feel good as humans that we're smarter than the average animal, right? Again, it's a power law and then another power law, right? Well, that's, that tells you the machinery operating here is somewhat different than the machinery that's operating there, but not grossly different. They have almost the same power law, right? Well, what about this? Here's body mass versus thigh bone size, bone diameter, bone length. Right? That's kind of amazing across all these different animals. It's a simple power law. The bigger the animal, you can just measure the slope, the bigger the animal, the bigger diameter the thigh is. Not surprising. And the longer the thigh is. So, what else can we learn? Humans like meat, they prize meat, okay? So if you go back 1.5 million years, back when it was Homo erectus, they were hunting the biggest animal there was, and they hunted them to extinction. So these great big mastodons, something like that, they don't exist anymore. They were wiped out by humans, right? And you come in more recently, like a couple 100,000 years ago, also hunting to get out the really big bulls and animals that were there. They picked the biggest ones and they killed them and they ate them. Well, there are reasons you can do that because it's efficient to get a bunch of meat and get together as a group and get a bunch of meat and hack it up and share it among the tribe and so forth. But even to the present, where we're down to wiping out things as small as gazelles, that's been going on. It's a pretty amazing power law. So if you look at what's going on, there were big animals, and there are not any big animals anymore, but a few places in Africa. They're sort of little reserves and slowly disappearing. Now we're doing this for fish. Almost all the big fish in the ocean are heading for extinction because they've been fished so severely, they can't get together to mate. They're so far apart, they're gonna disappear. So enjoy your fish now, because the big fish are gonna be gone, we're gonna be eating smaller fish. Right? What are the implications for health and aging? The answer is eating meat actually has some long-term effects on your health. And we'll see that in one of the charts I have, which carnivores don't live quite as long as herbivores, which is surprising too, because you think it's easier. Right? Here's another set of examples, the body mass versus the lifespan in years, and you see there's a general trend. It's not exactly power law, there are a couple different power laws, but that if you look carefully, the carnivores have got a little different slope than the non-carnivores, and the primates. So why is the primates don't fall down on the lower curve like the other carnivores? You know what's going on. And why is it clearly the birds are different from the other land animals, or animals, except for the birds that don't fly. The birds that don't fly tend to be down with the land animals. What is the mechanism going on for that? Well, the answer is pretty clear. If you're an engineer, and I said, make a plot that if I put a certain load on an electric motor, which ones are going to fail at which rate? The answer is very clear. Different motors in different circumstances last longer, carry the load and do it better. And you can just sort of look up things about why motors fail. And you realize different motors have different structure, that means the loads are different, the stresses are different, and so on. So if that means we got to look here for the differences to see what extra tools that some of the animals who do well have, so that we can make those and put them inside of ourselves as extra handy things. And you can either do that with CRISPR-Cas9, or you can do it by nanomachines that you put in. Nanomachines are just molecular machines. There's predictions of what the lifespan is versus what the lifespan is. It's a pretty picture so you can see what's going on. But one of the things that you see is the maximum lifespan is about equal to the minus half power for the basal metabolism rate. Okay, so why is it that way? Well, you got more mass, you got more sites for problems, but you got more mass, the signal, the surface area to volume is different, so you run your metabolism rate down. So you should expect that bigger animals will live longer because though they have more sites, they have lower generation of entropy rate. But it's a little trickier than that. Let me show you the next slide. You will notice how many of them die from cancers, the number 2 cause of death for humans, right? Well, these guys are 14%, a dog is 25%, humans are about 20%, but giraffe and elephants are only at a couple percent. What is it that giraffe and elephants do differently that causes them not to die from cancer? They found a different genetic fixing solution that prevents them from dying of cancer. Now it's more complicated than that, because when you look over here on this chart, here's the mammals on this side, and you look at the rate, elephant is lower than a lot of other things. There are some other kind of neighboring species that still have a high cancer rate. So the elephants have a particularly low cancer rate. Now you could have said, well, somebody's killing a lot of the elephants before they have a chance to get cancer, because cancer usually rises at roughly the 6th power of the age, and so forth. But that's actually not so true. You can compensate for it. And there are certain animals that have terrible cancer rates, right? And like chickens. And you can see. So if you look at this, that means there are extra mechanisms we can have if we can add them to the human. We can make the cancer rate for humans go down quite substantially. Why are these vegetable eaters? If they're vegans, they will tell you. But they have low cancer rates. And why does the rhino have a high cancer rate? Because its neighbors don't. It's biological neighbors. What is it different about them, right? And you can look at the various things and you can see, well, it turns out that the rhino, it's a complicated set of things about when rhinos get cancers. Right? The ones that live past a certain age, then they eventually get to the point where they start having cancer. So they have a mechanism that helps them for a while, and then it goes to the other kind of a situation. But these guys that are eating vegetables instead of meat, they seem to be doing better in terms of cancer. It's not a surprise. We suspect that humans that eat less meat, at least red-blooded meat, have lower cancer rate. This circle here is 60% death rate. So most of the stuff is down 10 up to 20%. The gorillas and the humans and so forth are up there, and the humans are actually still higher than normal for primates. So what is it special about humans? What do we do in either behavior or in genetics that makes us have more cancers? That's one of the questions we need to answer and fix. Health and lifespan, you can predict that. You can go say, you can make the energy production per unit mass and leakage, right, back into the cells, right? It's the number of masses that places go wrong. You can go through this kind of stuff and make a prediction. Think about what the mechanisms are and how you can fix the ones that are starting to go bad, because when the cells reproduce, they genetically, on the average, make one genetic change in the DNA, but also one in some of the other proteins and factors that are in your cells. And how are you going to do that? And how are we going to augment that? And how are we going to get these to reduce the internal entropy? So we're going to have the micro machines to do that. So here's some examples of how it's a little complicated. So in the upper right is how much muscle strengthening, like weightlifting and strength exercises you do per week versus what it does to your mortality. And there's the minimum, right? And if you look at it, that minimum is around 50 minutes per week, I think. That's a broad minimum, but it says when you don't exercise, your body doesn't know what's going on. So there's a trick going on. In your body, since every time your cell divides, it generally makes one mistake, there is a limit to how many times your cells can divide. And so you don't want to engage in activities that kill cells and cause them to, other ones have to divide to do it because it builds up. So what do you need to do? You need to do things that make the cell go to work to try and clean house and be better. Now when you do weightlifting, you have to damage a few cells. If you're doing strength exercises, you have to do enough exercise to damage a few cells. Those few cells rupture, send out molecular model signals to other cells and tell them to refresh themselves and tell the bloodstream to put in new, to build up the arterial system, so that if you ever do exercises, you will see you have trouble, you have trouble, you have trouble, you have trouble, and a few days later you can do it easily. And the reason for that is that's the point where the new vascularization is completed and it opens up, and now you have the capability of supplying energy to the muscles and you can do it. If you over-exercise, you damage too much and you put out too much of extra stuff. So if you under-exercise, you don't too. So there's an optimum amount of exercise you do, and those signals to the other muscle cells and to the blood cells cause the blood cells to also improve the circulation in your brain. It causes certain of your other cells to also try and clean house and fix themselves up. Exercise helps it so you don't fall down the stairs, but it also helps tell some of your cells to improve themselves. So the number one cause of death is coronary. And it turns out if you run a lot, you keep decreasing your chance of coronary disease. If you look at all diseases, you find out if you're doing over 33 meds a week, right, med hours a week. Now, med is your resting metabolism, right? When you're running, you're doing several, it depends on how hard you're running, you're doing several meds. If you're walking fast, you're doing 3 to 5 meds and something. So your minimum is somewhere near 33 med hours per week. That means if you're walking fast, say you're doing 4, that means you should do 8 hours of walking a week, for example. Or if you're running and doing 10 meds, you should do 3 hours of running per week. Unless it's your heart's the problem, then you should do a little more. It doesn't hurt to do a little bit too much, but it starts hurting in other areas. Right? So I have 2 different curves so you can see the difference between walking and the difference between running. She's clearly walking at the top one, clearly running at the bottom one. So the body is complicated. It has these compensating mechanisms where it tells cells either to atrophy and go away, or to be house cleaning and building their strength up a little bit because they're needed. And then that exercising and weight training, or the combination thereof, helps you if you do it at roughly the right level, not overdo it and not underdo it. Okay, what about food? Same thing. Turns out you already do this. You already do what's good exercise and not so. You already do. You should eat good stuff, right? You know, things like tomatoes and cabbage and all this kind of stuff. So if you eat too little, you know you get hungry and you don't do well. But if you eat sort of the right amount, it's okay. It gets you optimal tissue and organ function. And if you eat way too much, you got other problems. You get cardiac and other problems that come along. Now, there is an issue, which is over there on the right. If you starve lab animals or some humans, but not completely starve them, partially starve them, put them on a restricted calorie diet, they tend to live longer. That fits in my entropy as a proxy, because you have less food, you're generating less entropy that you're throwing in the environment, but you're also generating less entropy in yourself. But the question is this the right kind of life, right? That's a secondary question. But there are a number of longevity experts who are trying to put people on calorie-restricted diets. And yes, they do live longer, and it seems like a lot longer too. There is an issue that's the epigenetic part of it, which is you are what you eat, and what you eat affects how your genes are expressed and what things happen to you. This starts prenatal. That is, you want your mother and father to have been well fed and well treated, particularly your mother. And there is even tests done. So my thesis advisor's wife was a biologist, and she came up with all this big data, and she first showed there's a relationship between the fat level, the stored fat in a woman's body, and her fecundity. That is, she had too little fat, she was lower chance of getting pregnant. If she had too much fat, she was. If she has a reasonable amount of fat, then it was good, because that meant probably the rest of her diet was good, and therefore it was beneficial to have the children at that time. And so her data it's like, we're crying because her data signals and ways was like, the error bars are tiny, that the data was so So how come nobody noticed this, right? It's like, you gotta make sure that people develop right in utero and in their infancy and childhood, but also in adolescence, and then when they get older, they got to keep maintaining their muscle and physical capabilities, right? And then you can look at this prediction of how many people are gonna be age 65 and over, 85 and over, and you can see the prediction out into the future is that the number of people living longer is going to increase. And Hong Kong is a prime example of that. It's already losing young people, but as old people are not dying, they're staying around and having activity. Another way of thinking about how many problems. There's the system level kind of stuff, and here it's the interaction between the gut and the brain and the gut. It turns out there are tight links between them, and that affects your mood, it affects your health in other ways, and so on. And when there are problems in your gut from various things, it causes problems in your mental activities too, and vice versa. It's a thing that we know. Some people get very distressed and they get upset. They're a very good connection. But there are lots of connections like that. And then there's stuff that happens on the cellular level. This is cellular senescence. There are a bunch of your cells that no longer function well, but they hang around in your body. There's a lot of stuff that's happening. You have a lot of stem cells in your body. They're not completely stem cells, but they're not far from stem cells. Your bone marrow, for example, and that's producing your immune cells. You want those as close to the original as possible. So you need to be doing stem cell maintenance in order to make this work. And that's one of the things you have to track. And there's the intercellular, there's all kinds of things where there is information being passed from cell to cell, including cells sending material from one cell to another cell. And there's all those things you need to be thinking about and keeping track of. And up at the top of right is the telomere shortening. And I used to have a place for visiting scholars that I went to at Ecole Normale Superior. And Elizabeth Blackburn and her husband had the apartment next door part of the time. And I had arguments with her about if we could find ways to make sure that telomeres didn't shorten, would people live longer? Well, the answer is yes. There were some mice, they do live longer. But their risk of cancer goes way up. Because cancers are cells, they've learned to ignore the telomeres and reproduce that just continuously around. They're immortal cells in a certain sense. And now we found we have better tools to measure telomeres. Now we find that not all telomeres on each DNA should be the same length. They're all roughly half, but it moves up and down. But every time you divide, if there's any indication of an error, they take part of the telomere off, and eventually the telomere gets too short, and this DNA can't reproduce. And so there's a lot of different things that you're gonna have to treat care of. And a really big one is the mitochondrial misfunction. So I have this special slide for mitochondria that are near and dear to my heart, because they came from my mom. But they cause 40-something% of the things we call aging diseases. A lot of people here are doing research on Alzheimer's disease. It is clear one of the things that happens is as you stress your mitochondria because you make them overwork. And when they're doing that, they're producing radicals. They're producing chemical radicals that can do damage unless they get taken out of the mitochondria and out of the cell. But when a mitochondria goes bad and starts overproducing, there are molecules inside your cell that are supposed to go attach to your bad mitochondria, the gone rot mitochondria, and when they attach, they tell your cell to throw the mitochondria out of the cell. And when that fails to happen, you get Alzheimer's. There are other reasons you could get Alzheimer's, but that is one of the ways you get the plaque and the amyloid plaque and all that kind of stuff. It's the mitochondria doesn't quit doing its thing. It overproduces the radicals. It becomes a problem. But there's a bunch of stuff: heart failure, osteoarthritis, osteoporosis, all these things that we thought were other different kinds of diseases. They turn out to be driven by the mitochondria. So it's a very big factor in trying to understand and how to protect our mitochondria and make it efficient in order to keep our cells functions really well. Okay, and then there's the epigenetics. Epigenetics is how your behavior makes your genes do certain expressions. And so there are lots of things, and so this is a nice pretty picture, so I decided to use it. The epigenetics is basically what you're doing, drinking that Coke or eating too much meat or doing whatever, that causes your DNA to express a certain way. But these are things that when you change doing them, then your DNA goes back to doing the things that it normally would have done. Whereas if you break the DNA, then it starts doing stuff that it wasn't originally programmed to do. Maybe good or maybe bad, depending on what the DNA damage did. So you want to think about what these are, measure what these are, and be able to correct it. Now we have HKUST 9. We can go in and fix these if we know what the problem is and so what to do. The problem is you have to figure out how to go detect where it is, and then you have to send the right devices in to correct that DNA problem. And there's a bunch of, so this is, talking about the little methyl group that the bad mitochondria threw out and gets attached to your DNA and causes it to misexpress. Here's an example where people have gone and looked at various things like your liver, and that turns out to be connected to a huge number of things. If you look, there's just a huge amount of connection at the subsystem level, and you have to think about how they're going to go on it. But they're all going to end up being related to how the molecular machinery is working or not working. And so DNA single-strand breaks, there are mechanisms to go in there and fix that, and it's pretty good and pretty reliable because you know how the DNA strand's going to do. You can go along the DNA strand and say, well, what's missing here is an A or a G and A, whatever it is, and you put it in and it's done. But there are nucleotide excitation repair, that's a little more complicated, mismatch repair, where the DNA flips around and joins in the wrong place. But there are even some stuff for double-strand breaking. Now, double-strand breaking doesn't happen at all, but it does happen occasionally. You would think if you just have DNA, the DNA is no longer going to be able to split and make more. You need a mechanism that will come in and put the twisted pairs of DNA back together and have it work in order to sell. And evolution, or the machinery in humans, has got to the point where there are good fixes to that, but occasionally those things break down too, and you have to fix them and repair them. But mostly they work pretty well. And that's important because we're exposed to radiation in our environment. And neutrons and a couple of things can have double-strand breaks and things like that. So you need to be able to fix those. Life has known how to do that. So there are a lot of things you can do, but you've got to do a whole lot of things to make people be healthy. This is the life expectancy of women from 1840 to now. And you will notice that back in the old days, as it was engineering and civil improvements, we were gaining about 1 year of life expectancy every 10 years we lived. If you're a woman, you were expecting to die in 45 years back in 1845, but by 1900, you were up at 60 years. 60 doesn't seem like much now, does it? But if you look now, you see we're up to 85 years, a little more, it's 89 here. 3 dashed lines coming off of it. They were made in different years. Those were UN projections, the United Nations Studies projection, what life expectancy should do as much time, because there were certain diseases that people didn't think we could overcome. Well, guess what? We overcome when we blew through that. And then next time we overcome. And then there's a new projection. But here we have a projection. You're going to die when your entropy gets to a certain level, unless we go in and start fixing that entropy, right? And we'll reach a maximum. Okay. So this is impressive in a certain way, because we're gaining 2.4 years per 10 years. But how come this doesn't look like what we expect in the modern digital age? Why does it exponentially go up? And I believe the reason is people are impressed that they're doing this. They think that's enough. They're not thinking, I should be at the point where I'm gaining 10 years for every year I live, or 20 years for every 10 years I live. I should, gain 2 years, 2.4 years every 10 years is not. Well, that means you're going to die. If we don't accelerate up, then you're gonna die, right? So what are we gonna do to accelerate up? Well, we're gonna just move out of the way of the technology that's gonna let us live longer, right? That's why the human systems have to change and the laws have to change. Then people can live a long time. And here's another one. So I introduced one of the concepts that I forgot the exact name, but terminal life escape varsity. That if you are on the Earth and you get on a rocket ship that goes faster than 7 kilometers per second, you will have the escape velocity to go out into space and could drift on forever. Instead of having to go to death, you can just escape death. As long as you're gaining more years per year than you live in such a way, but also means we have to solve certain other problems. So here's an interesting thing. From 1960 to 2020, is life expectancy of men. I've been ignoring men in this thing. Women have better data, they don't get involved in wars and stuff like that. So it's a better proxy of how good health is doing. So French men have been improving their life expectancy quite regularly, pretty much like the women, but not as much, but not quite as much. But if you look at the Russian Soviet surrogates, Russia in particular, you find that when the Soviet Union fell apart, there were troubles, but when the Soviet Union fell apart here, the life expectancy of people went down a lot. It went down to 60. Right? There's a big difference between living to 75 and living to 60. 15 years if we want to do the math, right? Why did the Russians and the Ukrainians and the Kazakhs and the Estonians, why did they dip down so low? They went through a really pretty bad time. They went through a time when they didn't know if they had jobs, they had trouble getting food, the social structure was falling all apart, because when the Soviet Union fell apart, they didn't say, here's a plan to get to a capitalist system, or here's a plan. They just, started dividing up the spoils and everything fall apart. And because of that, people's life expectancy went down. Now, particularly men's life expectancy went down because in Russia and a lot of places, people were drinking a lot of vodka and doing a lot of things that weren't healthy for them. So their life expectancy fell quite dramatically. Now it's beginning to turn up again, except there's a new war, so this doesn't include them. So here is a curve. For young people, they have a lot of entropy going. They're making their bodies. There's a lot of entropy exchange. You just decide by yourself. There's a lot of stuff that happens here in infant mortality. And there were a lot of things that go wrong and they don't make it. Now we're getting better, so it's a little lower, but and then mortality rate is very low, and then there's this big shoulder that rises up and falls down. And so this particular paper that I took this from, they're proposing that there is a maximum entropy that you can live to, and that entropy then is, the proxy for the entropy is the age, but some people are generating more entropy in their body than others, so you expect to count the normal curve. So this is the normal curve, and the stuff between the normal curve and here is the premature mortality. Well, it is premature mortality in a certain sense, but you'll see in the next chart, it isn't. So these are women in Switzerland for which there were good data at this particular time. So you could see what the death curve was as a function of age. Here's some data from the US. And if you'll notice, 1933, it's this red curve. There's the infant mortality. That's the death. What you can see is the curve that's lower infant mortality, and the curve moved to the right in 2014. It sharpened up and moved to the right. There's still some, what you would call, if you thought the thing should be calcium in time, because there's just, when you get to a certain level of entropy in your body, you die, then you would expect a Gaussian around this point, which is at the max. But there's this tail out here. But if you remember, I told you, cancers and certain things like that, because there's multiple things that have to go wrong. It's like the 6th power of time. I claim it would go really as the 6th power of the entropy. So down here is an example of what a Gaussian, a 6th power of entropy Gaussian with a certain maximum would look like. And it doesn't look so different from that. So if we really push our medical stuff to the limit, we're gonna have a tightened up curve, but it's gonna have still some premature deaths, because occasionally you're gonna have several bad things happen at once, and you're gonna get cancer or you're gonna get something, you're gonna die. Right? That's the bad luck or the randomness of what's going on. But it's also complicated because not everything goes to the 6th power. Some of the things goes with different powers, so you need to add several curves together. Well, what about this? Here's just to be homage to Hong Kong. Here's from 2000 to 2023 estimate or something. Women's life expectancy and men's life expectancy. Why do women live longer than men? Is it because of behavior? Are Hong Kong men getting involved in wars? Are they drinking too much? What's going on here? Now, remember, I was showing you the curves that showed the more massive an animal was, the more, the longer the life expectancy should be, right? Well, here, men are bigger, and men actually have a higher metabolism than women. So they, in principle, should live longer except for the higher metabolism level. Men are bigger by almost 20%, 70%, and they have a higher metabolism by a similar number. Why is that? That means they have more matter, and they're producing more places for their diseases. And you just go ahead and put the numbers in, and you would expect that about 8% men should die 8% sooner than women based on that. And they kind of do. It doesn't come out exactly right, but it kind of does. And you can even see the dip for COVID, right? It's that you saw. So that's an issue. There are some behavior patterns, there are some other things, but a large part of that is that men just generate more entropy per gram in their body than women do. For some reason, men have higher metabolism. Now, that may be the main issue about having to be muscular and do stuff, but it's a more complicated kind of thing. I found a study that is studying the full life cycle of healthy people. And they have 220 participants, which is moderately large for a medical study. Most medical studies are way too small. There are only a few medical studies that have thousands of them. And what they've done is they've taken RNA sequences, DNA sequences, and over the life cycle of the whole set of participants. And they have frozen some of the cells from those people from different ages and have that information available. And they had 89% for extra validation of what's going on. Okay, now this is a data set that generally in medicine is pretty good compared to a bunch of the other stuff you can see. That's another one I've found on eye studies, but it's another thing. And again, it's just not very many. We have to study a huge number of factors. We have the genetic factors, the telomeres, the DNA. We have to worry about what causes senescence, that is, what causes cells to age and just be dead weight in the body and causing problems, or dying and taking a while to get cleaned out. We also have to worry about stem cell exhaustion. At some point, as people get older, their stem cells get exhausted. Now, one of the things that people don't usually know is you have T cells that are immune system cells. You start out with them pretty good in your 20s, but every 16 years you lose half of them because of genetic, effectively, some of them are still around, but they don't do their immune system function nearly as well. You lose about a factor 2 every 16 years. That's why who dies from pneumonia, who dies from COVID, it's older people, because they have a poor immune system to fight. If they get the same dose, they have a much less chance. We need to figure out put all these pieces together in the thing and then cross-correlate. There are a lot of data sets like this one and many other data sets that can provide us the information that's going on. We have information on other things. So, Farah got Nobel Prize for discovering the role of nitrous oxide in treating heart attacks and so forth. And then people have studied it a lot since then. The nitrous oxide really tells your cells, for the most part, to do good things to get healthy. So you want to eat a lot of foods with nitrous oxide, so down the right side. But there are a few things where nitrous oxide doesn't help you. You have to be careful about those. For a lot of stuff, for your stem cells, for your cardiac stem cells, for your epithelial ones, the NO helps quite a lot. There are a lot of factors, right? I mean, the problem is collect all the medical information and all the new data and the cross studies and put them all into the big AI model to see in the cross studies and then feed that back into the digital twin models. Because you're going to look from the embryo up to death, and you've got to track data over all that time period, and you're going to cross-correlate that and see which are the good things, and see how you can keep people at their peak where they're running with their briefcase. They don't have briefcases then. The genomes, the transcriptions, the proteins, all this stuff. But we can do all these things. That's the impressive thing. There's nothing here that we can't do and we can't improve on and do better. And this is a different way of looking at the issue. We've got a huge number of data sources. We're going to make virtual twins to people. We're going to run the simulations, and we're going to have life on one side and artificial digital you on the other side. The same thing is true if you look at the circulatory, all this kind of stuff. You're going to have the physical twin and the digital twin, and you're going to be doing assessments about what's going on. We're going to be able, within 5 years, if we have digital twins, to treat a number of diseases and prolong people's lifetime. And those additional 5 years or 10 years of life going to make progress in more areas so you get to treat more things and do things. So during being in the singularity, solve the problems from 5 years ahead. Think of solving new ways of doing things with the great new tools. And we can measure the genomics and the proteins in every cell in your body. Can't do it yet, but we should be able to do it within 5 years. So that's pretty intrusive, but it's a pretty good way of tracking what's going on. And your digital twin will know you're aging in health state better than you will, right? And we'll be able to go in and repair the damage, particularly the damage repair mechanisms, and we can make people younger and healthier. 2 weeks ago, or a week and a half ago, a talk by a person from Tencent, Professor Chen Yu, who talked about doing single cell sequencing for DNA and proteins at the health safety ceremony. And he's one of the companies that are building the tools for being able to do these things that we need to be able to do. People are already building the tools that are necessary. You're also going to need to be a cyber you. When the set of people known as masters of the universe, when they started, the average holding time for stock or some kind of equity was 4 years. By the time the masters of the universe were at their heyday, the average holding time for a stock was 22 minutes. Nowadays, where are the masters of the universe? Well, now there's high-frequency trading. High-frequency trading, the average holding period is gone to less than a minute. Generally, the holding time period is between 1,000th of a second and a couple of minutes. Okay, that's way faster than the masters of the universe could do it. So what do the masters of the universe do now? Well, they kind of know, it's like George Rose forced England to devalue the pound. It's done a different way. Machines do that now. The humans are giving guidance. I got an interview from Renaissance Technology in 2008, which it was a big crash. And when they were doing my interview, they had to run off because they had to rewrite all the code because certain stocks were not allowed to be shorted anymore. It was an interesting phenomenon. And they were doing complicated stuff, but they had to put in rules, the 3-5-7 rule, so you can remember it. Never bet more than 3% of your capital on any one trade. Never have more than 5% of your capital in open trades, and make sure that your winning trades give you 7% more than your losing trades. And then trade 1,000 times an hour, all day, all week, right? And you're a master of the universe computer. So James Simons, who was the one mathematician who started that, and I knew it because he gave money to Berkeley, to the Mathematical Sciences Research Institute, to build a big auditorium where I gave some talks. We call that MISRI for short. Mathematical Sciences Research MISRI. You had to be there. And anyway, he was the one smart enough to move his computers closer to the New York Stock Exchange, right, and closer to other stock exchanges, because they didn't want to use those extra milliseconds because other people would see them driving their trades and try to interfere with their trades. So they wanted to get the trades done before the other people knew a trade happened. But he's the one that did really simple thing. He just said, this is a stochastic process. Wherever you are, it's a random jump to wherever you're going to go next. You don't just randomly pick stuff out of the sky. Wherever you are, you jump a little ways from that. That's what happened. When he put that in, their trading success rate went up, and he for a while was the 20th or 22nd richest man in the world. You realize, yeah, it's getting way cheaper, and it's going to be a lot better in 2 years. And it will be AI attacks on your identity. They're going to want you to get your digital self, as well as all of your resources. And those attacks are going to be powerful, and they're going to come in a few milliseconds. How are you going to protect yourself against that? Well, the answer is Cyber U, right? Cyber U is there protecting yourself. That's what you have to, that's why you're going to have a Cyber U. And so there's going to be a lot of processes in the world in very few years, like 3 to 5 years, which are going to be very powerful and very fast. And the Cyber U better be very powerful and very fast too, to keep you protected. That's why you're going to want a digital twin that's more than just a physical model. It's got to know what you want to buy and when you want to buy it, and who's attacking you that isn't you. Right? In the future, we're going to have digital twins, and it's going to be the digital representation of you. It's going to be both your twin and your digital agent. And then it was the one that's going to handle your interactions with the too fast, too smart world. And you're probably going to have swarms of digital agents working for you. They got to know what you want to do. Anyway, that's the masters of the universe are no longer masters of the universe. The digital guys are going to be the masters of the universe. Okay, so that's the end of my talk about digital twins.